you know if you start with reactants and only reactants, then some of your reactants have to turn to products to get to equilibrium, and vice versa. If you only start with products, some of your products have to turn into reactants to get to equilibrium. But what if you start with both? What if you start with some amount of reactants, some amount of products, and you want to know what your concentrations are going to be at equilibrium? Well, then you don't know if your reactants will turn to products or if your products will turn to reactants in order to get there. So you have to ask yourself, you have to question, am I at equilibrium? And which direction do I need to proceed to get to equilibrium? So I try to remember that cue. You know, I'm questioning, am I at equilibrium? And that Q is the way that we represent the reaction quotient. The reaction quotient is, it's questioning, am I at equilibrium? And all it is, it's the same thing as KEQ, except for KEQ, you plug in values when you're at equilibrium. And for just plain Q, you're finding out if you're at equilibrium. So if I'm starting with these three concentrations, I just plug them into the reaction quotient, and I'll find out if I'm at equilibrium or not. Basically, if Q equals K, then you're at equilibrium. So let's see, it's going to be the same setup. So it's the same thing. Let's say that I have this reaction that A is turning into 2B. And so I know the K expression is going to be B raised to the power of 2 divided by A using concentrations. Q is the same thing. I'm questioning if I plug in the current concentration of B raised to the power of 2 divided by the current concentration of A, am I at equilibrium or not? So I get this value, and you can see if Q equals K, yes, you're at equilibrium. But if Q's too big, well, it's products over reactants. And since it's products over reactants, well, then we know if Q is bigger than K, it's because you have too many products, right? So too many products. And if there's too many products, then you know the reaction's going to proceed turning products back into reactants, so you proceed to the left, right? And then you know that if Q is less than K, well, if Q is less than K, it's because you don't have enough products. So in that case, there's too few products. And the way this reaction's going to, the way the system is going to adjust is that the reaction is going to proceed forward. So you're going to be turning some of the products, or some of the reactants into products. Right? Reactants turn to products, and here when Q is bigger than K, then the products are turning into reactants to get to equilibrium. And if you plug in these are my current values, I'm questioning if I'm at equilibrium. If Q equals K, well then you're at equilibrium. Okay. So what Q tells us is it tells us, are you at equilibrium or not, and what do you have to do to get to equilibrium? So let's try one. I have the same reaction we had before, so I have the same K, we'll assume it must be at the same temperature. And I'm going to have a 1 liter container with 2 moles of hydrogen iodide and 0.5 moles of hydrogen and iodine. I want to know if the system's at equilibrium. I'm questioning if I'm at equilibrium. So I'm going to plug it into my Q value. I'm going to plug into the Q expression and see if I'm at equilibrium. And if I'm not at equilibrium, I want to see what I need to do to get to equilibrium. So first let's question, am I at equilibrium? So it'll be concentration of hydrogen iodide, which is 2, raised to the coefficient 2, divided by concentration of of hydrogen, so 0.5, and multiplied by the concentration of iodine, and that was also 0.5. And I'm saying concentration because it's 0.5 moles per liter. Okay, so 2 times 2 is 4, 1/2 times 1/2 is 1/4. So 4 divided by 4, I have 16. So Q equals 16. Q doesn't equal K, so I know I'm not at equilibrium. And I can see that Q is actually less than K. Since Q is less than K, it's because I don't have enough up here. I don't have enough products. So I know that I'm going to proceed to the right. I know some of my reactants are going to turn to products in order to get to equilibrium. And let's see how much. So if I'm actually going to calculate the new equilibrium concentrations, this is that style of problem again where we said of the 3 things, initial concentrations, equilibrium concentrations, and the K expression, you're given 2 of the 3 things, or K value. You're given 2 of the 3 things and you have to solve for the other. we're missing equilibrium. So the first thing I want to do, I'm going to write the equation, and I'm going to put it here just so I can write underneath it. Give myself some space. I also said that I should write the K expression. So I know that K is equal to the concentration, equilibrium concentration of HI squared over the concentration of hydrogen times the concentration of iodine. So I have that information. And now I set up the ICE table, my initial change in equilibrium amounts that I know. And what I do know is I know that I have 0.5, 0.5, and I know I have 2. I also know that I didn't have enough products. So I'm going to lose from this side. I'm going to lose one of these for every one of these. And for every one of these that I lose, I make 2 of these, just using stoichiometry, so plus 2x. So I still have these unknowns, 0.5 minus x, but at least the one thing that I don't know is just x everywhere. So if I can figure out x, I can answer everything with respect to this problem. Okay, so I've got my equilibrium values. I have a way to relate them. I can plug them into here. So I'll go ahead and do that. I know that 55.64 is equal to the concentration of this guy, 2 plus 2x squared. And that's divided by 0.5 minus x times 0.5 minus x. I'm going to go ahead and write that as 0.5 minus x squared. Okay, so once again I can see, conveniently enough, I have a perfect square, so I can square root both sides. We'll do that. And this ends up being 7.459, or is it 549? Magic. Yep, 459 is equal to 2 plus 2x over 0.5 minus x. So now I'm just going to do some algebra. I want to go ahead and get this out of the denominator first, and then the goal is to get x alone. So I'll multiply 0.5 minus x times this guy. And 0.5 times 7.459 is going to give me 3.7295. And this x, so minus 7.459x, is all equal to 2 plus 2x. All right, I'm going to gather like terms. I'm going to add 7.459x to both sides. So when I add to this, that just ends up being 0x on this side. And I add to this, I'll get 9. 7.459x plus 2x. 9.459x. I'm going to subtract 2 from both sides. So 2 minus 2 gives me nothing without an x over here. And 3.7295 minus 2 gives me 1.7295. All right, now I want to get the x alone, so I'll divide both sides by 9.459, 9.459, and I end up getting that x is equal to, I get 0.1828, except I wrote the problem with only one sig fig, which is bad. Okay, so, but that's what it is. So it's just going to be 0.2 when I use sig figs. All right, so that's my answer. That's x. So that means if I plug that in for every place that I have x, I can figure out the equilibrium concentration of hydrogen, the equilibrium concentration of iodine, and the equilibrium concentration of the hydrogen iodide. And what I should do, I should go ahead and plug everything in and make sure that when I plug in these equilibrium concentrations that I calculated, that when I plug them into the expression, they really do equal 55.64. So I will go ahead and do that. So I know that I have 2 plus 2x, x being this value. When I plug that in, I'm going to get I'm saying that 55.64 equals 2.366 squared. So that's going to be 2 plus 2 times this, divided by, I'll go 0.5 minus this, and 0.5 minus the 0.1828 gives me 0.3172, and that's also squared, this whole value. And when I type that in, I end up getting really close to this 55.64. So yes, my X works, and now I know all the equilibrium concentrations.